I want to do some quick examples now, introducing some multiples as well. So in this first one, I'm adding my A vector, which is again in this case going to be some unknown vector, I'm just working with variables, plus twice my B vector, and I'm going to call the sum C for obvious reasons. So in this case, what I can do is take my previous result, that my C vector is going to be equal to my A component vector plus my B component vector, but now that 2 actually is going to be distributed to both component values of my B vector. And again, keep in mind that each of these components could be negative. So that's all you have to do. So if you have a scalar, keep in mind that it goes to both components. Now what if instead we have a negative value? And again, keep in mind that either of these component values themselves could be negative. They're not truly a magnitude since there's a sign. And in this case, we again distribute it, right? So that's all. That's all there is to it. And so anytime you have a value here, you're going to distribute it. It could be a variable itself. But what happens if we have a minus sign here? Well, that minus sign is, adding a minus sign is the same as subtracting. So secretly here, perhaps not so secretly, remember that this is just your vector subtraction. So how we had been subtracting vectors was to add the negative. So this here is the same thing as saying A minus your B vector equals C. All you have to do is subtract your B components from your A components. So that's not too bad. So one thing that I want to talk about briefly and do an example on is the idea of flipping a vector. And we've talked about this before in the idea that if I have my C vector going this way, my negative C vector looks like that. And so what we actually are doing in this case is basically multiplying it by -1, right? That's what we had said subtraction was taking our vector and flipping it, which is the same as the minus sign. So again, all we have to do is distribute this minus sign on each of the components. And so we see that now our flipped vector is going to have negative each of our components. So where this is really going to come in is, again, in subtraction, but we also want to make sure that we understand what's happening to the signs here if our initial vector isn't in the first quadrant. So let's pick a C vector that's actually in this situation where we have that C vector is equal to -4 in the x hat direction and -2 in the y hat direction. So in this case, if I want to flip it, -C is going to be equal to -4 in the x hat direction plus -1 times -2 in the y hat direction. So the -C vector is equal to 4x hat plus 2y hat. And what that's going to look like then is, if I actually didn't draw enough of an axis, but flipping this would look like that. And if you imagine taking that and grabbing it, it's going to go over there into the first quadrant. So again, please keep in mind, I realize that I haven't quite shown you that explicitly, that the Cx or the Cy value itself can be negative, that it's coming from the projection onto that axis. So if in this case, your Cx component vector is pointing to the left, that means that you need to have a minus sign in your x component, as we did here. So please be careful about that. I want to show you that everything we've talked about so far extends as far as the math will take you. So this is again why when we're working with kinematics and forces, you need to work separately with the x and y components, but mathematically, once you've done that, everything works out. So let's say here that we're actually adding 3 vectors to get a 4th vector. And we know in this case 2 of the ones on the left and the one on the right by itself. So we're looking for one of the vectors on the left. So the good news is that the way that you would rearrange this, if these were just simple numbers or if these were simple scalars, that still works. We can move a and b to the right side, leave c by itself, and so we're left with this. What we now can do is break all of this into components, and this equation is still true if we have our x components and our y components. So the x component of c is equal to d minus a minus b, where those are all the component values, and same then for the y components. So whenever you're working with vectors, you can work with vectors in an algebra way, that's fine, but eventually you're going to need to break them into components to actually do the math. Again, something like this is possible to do graphically, but usually you're not going to have the accuracy that you need. So to really summarize what we went through, the thing that I want you to know and remember the most is that you always need to add and subtract vectors when they're in their component forms. Never add or subtract vectors when they're in a magnitude and direction form. Please don't do that. It is definitely going to give you the wrong answer. So if you have any scalar multiples or minus signs, you just distribute those to both of your vector components. Again, keeping in mind that your vector components themselves might be negative if your component vector points in the negative direction. Don't mix your x and y components together. If you look back, anytime I have x and y in the same equation, at that point it's a vector where I've actually added the hats there, my unit vectors. So if you just are working with scalar equations, have x separate from y. So the last thing is that your mathematical operations, again, can work as normal when you're working with components in one direction, but make sure again that you have all one direction such that all of your components are x or in y. Again, these things might seem okay, but once you're trying to do the math, typically this is something people aren't careful about. So please be careful about that. And if you want to practice breaking things into components, you just want to think about trig. So go back and watch the trig videos if that's something you don't feel comfortable with.